Hi everyone, welcome to day 4 of the polynomials unit. Today we are going to find all real and complex roots of a polynomial. We haven't looked at any complex roots yet, and then we'll write the equation of a polynomial as a combination of linear factors. So let's get started right away. You see this first example is going to be a review of factoring, but I don't know if everyone remembers the factoring rule for a sum or difference of cubes, so I placed it here. You can tell something is a sum of cubes when it has or a difference when it's got two terms and they're both perfect cubes. So x cubed is a perfect cube and 8 is a perfect cube. That is 2 cubed, by the way. So you can go ahead and solve this whole question by factoring, get as far as you can, and then pause the video. When you unpause, you'll come back and the solution will be there and we'll go through some of the interesting parts of it. All right, so here are our solutions. We have two perfect cubes, x cubed and 8, and we cube root them to get x plus 2. And then we square the first term, square the last term, and multiply them together in the middle. Remember, we have SOAP is one way to remember the signs. Same, opposite, always a plus. And so it was the same, it was opposite, and then it's always a plus. So here are our solutions. Set each factor equal to 0, x plus 2 equals 0, x equals -2. And then here you can't factor this, so you have to use the quadratic formula. And I want to see how far you guys could get here. We get a negative under the square root. You have seen this before, so remember, this is not a real number. You can't square root a negative, but it is imaginary. So what we do is we simplify it by taking out the I. For imaginary, that's the square root of -1. Factor it out, square root it out or whatever, and then we still get a solution 1 plus or minus I square root 3. So let me give you guys a second to look that over. Correct yours if you didn't get that and update it. And then we need to talk a little bit about what this I situation is. So if you think about what we've been learning so far, we have this one rational solution and then two irrational ones. But the difference between this and what we've been doing is that if we were to graph these, we always should have our 3 total roots when there's 3 as the degree. And then here again, I'm going to say that we have one rational root, but I'm going to add the word real to it. We have one real rational root, and then the other two are imaginary. Or not real. Or complex. Those are all things we like to say for the same thing. And so that means they don't show up on the x-axis. So they are not x-intercepts. But they still are roots. So I'm just going to keep that underlined there. They're still roots, though. So we still have that. And they don't show up on the graph, as you can see. Only the one real rational root shows up. So that means that we're still going to do everything the same that we've been doing, but we will continue if we get a square root under a negative. Let's talk about what that is for a little bit before we get too far into it. So the square root under the negative, like I said, is called complex number or imaginary. And so the square root of -1 we represent with the letter I for imaginary. And that means that if we were to square both sides of this equation right here and then have I squared would equal -1. So that's important for operating and for solving when we write the equations later. And so it is kind of a silly concept in math to think about, imaginary numbers, like, oh, cool, so we're doing stuff that's imaginary now. You can't get any less relevant. But Imaginary numbers really are used in a lot of computer science type of programming and stuff, and so they are relevant in the world. It's just not something you might see every day or out in nature. So the standard form of a complex number is a mix of a real number and an imaginary number. So we write it like a plus bi. We always like the real number to come first, and then the imaginary to come second, and then a and b are just coefficients or constants. So here's a quick example of how to operate with imaginary numbers. They really work just like regular variables or regular numbers, except for this fact right here is going to be very important. So what I like to do is I like to use a box to multiply because it helps organize it, especially since we do have to substitute the I squared for -1. So I write 4 plus 7i up here, and then 1 minus 6i down the side. And then we just multiply it all together. 4 times 1 is 4, 7i, -24i, and then here we have -42i squared. But remember, I squared is -1. And so I'm going to replace this with -42 times -1, which we can multiply those two numbers together and get positive 42. So I don't like to look at that. I would just write positive 42. And then when everything's in my box all organized, I like to put the real numbers first. So that's 4 plus 42 first. Let me get a color change here. So we're going to do 4 and 42. That's 46. And then we will add the -24 and the 7. And so this is our answer. Like I said, they work just like variables, but the I squared equals -1, so we can substitute that out to finish simplifying. Okay, so a couple more things about them. Complex numbers we're going to refer to as irrational solutions, and that's because they are square roots. So remember, I equals the square root of -1, and so it follows the irrational properties. So what that means is that whenever we solve a square root, we do a plus or minus, and so they come in conjugate pairs. Conjugate is where the middle sign changes or the sign in front of the irrational number changes. And so 4 minus 6i will have a conjugate pair of 4 plus 6i. 3 plus I will have a conjugate pair of 3 minus I. 2i could also be -2i because we can write this as 0 plus 2i, and so it can be 0 minus 2i. And then, like I said, the square roots and the i's are going to have really similar properties. So 2 minus square root 3 is the same as 2 plus square root 3. Not the same as, but they go together. And that's, again, like I said, when you solve for these, you typically are using the quadratic formula where there's a plus or a minus when you're square rooting. And so that means if you have a minus, there's also a plus. If you have a plus, there's also a minus. They come in pairs. If we look at that a little further, that means there's always going to be an even number of irrational solutions because they come in pairs. Because pairs. Pairs means 2. And then if a 0 of a polynomial is irrational, then the conjugate pair will also be a 0. So if I know 4 minus 6i is one of the solutions, I also know automatically that 4 plus 6i is a solution. So that kind of stuff helps us as we look at different solutions and try to build polynomials from it. All right, so that's enough about just background information on complex numbers. Now we're going to continue solving. And so we're going to do one with 4 zeros. We have find all solutions. And so that's going to include real solutions and complex solutions. So the first thing we do is we make sure it's equal to 0. All right, we did. Great. Next, we graph it. We can use Desmos to graph. I like Desmos. It shows everything the easiest, I think. And so I graphed it, and we find the real rational zeros. So what I can see from this graph, and you guys can pause and check it yourself in Desmos if you'd like, is that -6 is a solution and 1. Those are our real rational zeros. So They cross at the x-axis, and when I click them on Desmos, I can see exactly what they are. They're not never-ending decimals that I can't figure out the exact value of. Those are our two real rationals. Step 3, use synthetic division to reduce the polynomial to a quadratic. So what that means is I start with my root 6. I had to start with this one because it's first. You can start with either one. -6, I'm sorry. And then we list the coefficients. So 2x to the 4th, 8x to the 3rd, -19x squared, 27x, and -18. And then I bring down the leading coefficient and do synthetic division like we learned last class. So bring down the 2, multiply, add, multiply, add, multiply, add, multiply, add. Which I love synthetic division. I think of it like it's like a little puzzle, a little game. Well, I think it's fun anyway. So what we do next, we haven't done this yet, but we put the next 0 on the line with the coefficients that we got after our first round of synthetic division. And now we're going to divide this polynomial by 1, x minus 1, synthetically again. So we just repeat the process, but we use those same numbers that we just got. So it's just a fluid thing. Bring down the 2, multiply, add, multiply, add, multiply, add, and we get 0. Remember, you'll always get 0 as your remainder when you're dividing by a 0 or a factor of the polynomial. And then now step 4, find the remaining zeros with the quadratic formula. So remember, this is 2x squared minus 2x plus 3. And we use the quadratic formula. X equals negative b plus or minus square root b squared minus 4ac all over 2a. So we'll keep going. And we'll simplify negative square root negative 20 to be 2i square root 5 all over 4. And our final thing is that we can simplify all of this by writing 1 plus or minus, let's make myself some more room, 1 plus or minus 1i square root 5 all over 2. No room down here. And then we also have -6 and 1. So here we have our 4 zeros. 1, 2, 3, 4, because it was to the 4th power. And these are always coming in pairs because of that plus or minus when you use quadratic formula to solve. Okay, so that is just how you find your complex. The nice part about it is it's really not that different from what we did last class. It's just that you sometimes are going to be square rooting and negative, and so you have to write that answer as an I, or a complex solution. Okay, so let's look at the last objective for today. Right